And with that, good morning everybody. Welcome back to Calc 2. Plan for today, got the standard 4 quiz ready for you. And then we are going to jump into standard 5, start talking about inverse string functions. As far as office hours go, I've got my usual office hours today at 11 and at 1, as well as tomorrow at 1. As far as homework goes, I posted another web work assignment, homework 7, which will be due on Monday. And also, don't forget you have a web work assignment due Friday. Nothing due today. Any questions or comments before we get started for today? When given the choice between ham salad and eternal bliss, what would a mathematician choose? Donna?
Ham salad.
Yeah, ham salad every time. Why? Because ham salad is better than nothing. Nothing is better than eternal bliss. Therefore, ham salad must logically be better than eternal bliss. And with that, go ahead and pass out today's quiz. So go ahead, take a few minutes, and good luck, you guys. go ahead and take a few seconds to finish up your thoughts. And pass your quizzes in, please. Alrighty. So, talked about a lot of integration techniques thus far. We've done kind of a review of some of the Calc 1 standard integration techniques like reverse power rule. We've done some U substitution. We've done some integration by parts. We've done some partial fraction decomposition. And I'm going to put what we've looked at to the test before we start our next standard. So, I want to find the area of the circle. We're going to have a goal. Let's prove the area of a circle of radius r. What would we like to have the area of a circle be if we had a circle of radius r? Who remembers their geometry formulas? Ned?
Pi r squared.
Yeah, I'd like it to be pi r squared. Where if r is measured in units, then pi r squared, the area is measured in units squared. So here's what we're going to do. We're going to graph the circle of radius r in the xy plane. If we have a circle of radius r, how can we find a formula for that circle in terms of, as an expression in terms of x and y? Kathy?
X squared plus y squared equals r squared.
Yeah, we would get that x squared plus y squared is equal to r squared as a formula for a circle of radius r. Which if we then wanted to go and solve for y, would give us y squared is equal to r squared minus x squared. And if y squared is equal to r squared minus x squared, Nathan, what would y be equal to?
R minus x.
Not quite.
No.
Can't simplify quite just by taking the square root of each term individually.
Square root of r squared minus x squared.
And it's going to give us the square root of r squared minus x squared. Almost. Theoretically, y could be negative, which would give us y could also be equal to the negative square root of r squared minus x squared. Because if you square both sides, if you had a negative sign here, the negative would cancel out and still leave us with r squared minus x squared. So integrating a plus or minus expression sounds difficult. So would everyone be okay if instead of trying to find the area of the full circle, we just find the area of a quarter of the circle and multiply by 4? Due to the symmetry of the circle, I would say if we can find the area of the circle that's in the top right, that's in the quadrant 1, the top right quarter of the unit circle. If we quadruple that, it should give us the area of the overall circle, which would tell us that our area should be equal to 4 times the area of top right circle. And with that in mind, how can we set up an integral that'll tell us what this area is going to be? Well, we know that the definite integral of a function will give us the area under that function from point A to point B. So what I propose that we do is that we can take an integral of our y function, which for only looking at the top right corner will give us the positive square root of r squared minus x squared. What are going to be the bounds, Jonah, on our definite integral?
Would it be x and y?
Oh, we need between two x values. The x value on the left-hand side of the shaded region to the x value on the right-hand side of the shaded region.
Would it be 0 and 1?
Like 0 on the left-hand side. No, I don't think it's necessarily from 0 to 1.
Pi?
I don't think it's from 0 to pi. Pi?
Pi halves.
That can be from to pi halves. Nora?
Would it be to R?
Yeah, it's going to be to r. Because if we have a circle, x squared plus y squared equals r squared, the far right point of the circle is at an x coordinate of x equals r. Who to pick on. Already called on you, right? That sort of scared look away would make me want to call on you. Reagan. Does it look like a u substitution would help us evaluate this integral?
Yeah, if you make u r squared minus x squared.
Awesome. So if we let u be r squared minus x squared, we'll get du is equal to negative 2x dx. Is that a substitution we can easily make into this integral?
Yeah.
I think the problem is this x term. In that I don't know kind of where the x term would come into play. If we had like something like x integral of r squared minus x squared dx, then we could multiply both sides by negative 1/2 and replace x dx with, say, negative 1/2 du. But unfortunately, we don't have an x term there. So I think that's going to be out. Nolan? Does this look like something to try integration by parts on?
Sure.
Cool. What's your u and what's your dv then?
No. Wait. Yeah, you could do.
You're having funny reactions, I hope you know.
No. Well, you don't have two things multiplied by each other.
And not partial fractions. Integration by parts is usually used when you have one expression multiplied by another expression. Well, here we just have square root of r squared minus x squared. It's not really being multiplied by anything. So it's not clear to me how integration by parts would help us out here. Miriam, how about partial fractions? No, she's not here. Let's call on someone who's here. Mary, how about partial fraction decomposition?
No, it isn't a fraction.
Yeah, This doesn't really look appropriate for it. That's like when you have polynomial divided by polynomial. Well, this is just as a square root of a single thing. Integration techniques don't seem to be super helpful here. I think.
Could you multiply it by something like that equals 1? So you could like multiply it by like square root of r squared minus x squared over square root of r squared minus x squared.
Okay, so that would transform it into, that's where I got 4 from. R squared minus x squared over square root of r squared minus x squared. That look any easier to integrate? Well, we have a fraction now. Still doesn't look like something we can do partial fractions on because of the square root. And I still don't think u sub would be particularly helpful. If we tried u equals r squared minus x squared, we'd get u equals, we'd still have the problem of we'd have an x dx instead of like an x squared or an r squared minus x squared dx. So I think you could certainly, Bethany, do what you suggested. I'm not convinced it's going to be particularly helpful for us. But I like the idea. So, we seem to be stuck. So, what we're going to be doing for the next standard and a half is we're going to be coming up with another integration technique that's going to allow us to evaluate integrals that look like this. Integral of, say, square root of r squared minus x squared, which, as of right now, we don't really have a good technique for being able to handle integrals like that. And so, yes, Christopher?
I'm a little bit confused about why we can plug in what y equals for the entire area of the top right corner.
Sure. So, would you agree that this is the that this gives us a formula for the full circle?
Yes.
So, I would say on the top right corner, this piece right here, we can say, using kind of this little bit of algebraic manipulation, y is equal to square root of r squared minus x squared, where that just comes from solving this equation for y. In order to have x squared plus y squared equals r squared, y would have to be equal to square root of r squared minus x squared up here. We also have a plus. With Dr. Gerstle, we have a plus or minus. The minus part of this square root comes from looking at the bottom of the circle. If we're only looking at the top of the circle, then we can just use the positive square root instead of the negative square root. So the whole idea here is we have a curve, y equals square root of r squared minus x squared. We want to find the area trapped underneath that curve. And kind of our technique, our Calc 1 technique for finding the area under a curve like this is to just do a definite integral from the left endpoint, which is at here, at x equals 0, to right endpoint at x equals r. Does that sort of answer your question?
Kind of. I'm just confused why, it might be like a terminology thing. Why does y equal that curve rather than just the coordinates for the magnitude of y in the circle?
Because the magnitude of y in the
So,
circle. I'm sorry, I'm not sure what you mean by that.
So like x squared
Mhm.
to me is equaling literally 0 to r.
Mhm.
And why does y equal r squared minus x squared under the square root rather than just the same thing but in the y direction?
Okay, why are we solving for y equals
Yeah.
expression for x instead of x as an expression of y?
Right.
We could do that, actually, if you wanted to. We could just as easily, if we solve this for x, we would get x equals square root of r squared minus y squared. And if we really wanted to get cheeky, we could write this as an integral from 0 to r square root of r squared minus y squared integrated with respect to y instead. And that would actually give us the same result in the end. It would give us the same result once we multiply it by 4. So why are we choosing to solve for y instead of choosing to solve it for x? Mainly because that's the integrals that we've been focusing on in this course so far, as well as in probably the ones you saw in Calc 1, are trying to write y as an expression in terms of x usually, and then doing integral from x equals 0 to x equals r of our y as a function of x, rather than say trying to integrate from y equals 0 to y equals r, x as an expression in terms of y. If you really wanted to go that route, you could. It's basically the same integral, just you're replacing your x's with y's, but you would go about solving it the exact same way. Hey, Joy, any questions?
Why I'm just gonna say maybe you could divide by r squared.
Divide what by r squared?
Like, you could do like the r squared divided by r squared, like the entire thing within to the 1/2 divided by r squared, so you get like 1 minus x squared over r squared, and then maybe you could do a u sub from there.
Okay, so you want to like factor out and like square root of r squared from the denominator? Sort
Oh,
of?
not that one. I'm sorry, the original one, not the one.
Back here?
Yeah.
Factor, so we could certainly do like I think we certainly could do something like, we could factor out square root of r squared and get square root of r squared times square root of 1 minus x squared over r squared. And then square root of r squared just becomes plain old r. Is that what you were suggesting?
Why can't you just do it within the square root?
Okay, so just like that.
Not really.
Would you like to come up and show me what you're talking about?
Well, it's not much different, but if you could like within here, and then you would have just like do that, like within here, not but and then it would be like 1 minus that over that, and then you get u sub that, and it would just be u squared within that. Is that a lot?
Okay. Okay, I got you. And let u be something like x over r, and then
Yeah.
you can divide by r squared here, multiply by r squared, which I think would give us something very
Yeah,
similar to this. Sure, you could do that. Do you know how to integrate square root of 1 minus u squared?
I don't know.
I was going to say, if we knew how to integrate that, then that would certainly be helpful. And in fact, what we're eventually going to do is going to be very similar to that. But right now, similar to what Bethany suggested, it's certainly something we could try. I think it's a great idea. I'm just not convinced it's going to be super helpful for us at this point in time. So, turns out we're going to need to use some of everybody's favorites to help us out here. We're going to need trig functions. And not just trig functions. We're going to need the help of inverse trig functions to help us out here. Yes, Mary?
Could you repeat why x squared plus y squared equals r squared?
That's just the general formula for a circle. That's the set of all points in the xy plane whose distance from the origin is equal to r. It's similar to how, like with the unit circle, we have like x squared plus y squared is equal to 1. Or on the unit circle, you could even say something like cosine squared theta plus sine squared theta is equal to 1. That's just kind of a general formula for the unit circle, right? Or using the Pythagorean identity. If you kind of generalize this to a circle of radius r instead of a circle of radius 1, you get x squared plus y squared equals r squared instead of the 1 squared. Usually this is a 1 squared, but 1 squared just is 1, so it doesn't really matter. All right, so time for a new packet. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. So we're going to table the circle problem for now and come back to it once we have a little bit more machinery to work with. But what we're going to be focusing on in this packet is we're going to be focusing on doing sort of a review of what are the inverse trig functions, talk about how do we differentiate them, and then talk a little bit about how can we use inverse trig functions in order to help us integrate something. So first of all, what do we mean when we talk about an inverse function in general? So those of you who are in my Calc 1, we talked a little bit about this in the middle of Standard 9, I believe, last semester, where we had two functions that we've used quite a lot, both in Calc 1 and in this course, that we said were inverses of each other. Somebody remember, or somebody know what two functions I'm referring to? James?
Are you talking about derivatives and integrals?
Not particularly at the moment.
Okay. I can't remember what it was.
But said we had two functions that sort of undid each other, so to speak, back in the days of Calc 1. Or if you do one function and then another, you just end up back with plain old x. Nora?
Wasn't it the natural log of e to the x?
Yeah, natural log of x and e to the x were kind of our go-to examples in Calc 1 of inverse functions. So just to do a little bit of review, our idea behind inverse functions is if we had a function like f of x equals e to the x, we could say that the inverse of x equals natural log of x. And the whole idea behind working with inverse functions is you want functions where if f of a is equal to b, then f inverse of b should be equal to a. So essentially, you're taking your x and your y coordinates with an inverse function, and you're swapping them. The x's become y's and the y's become x's, but they satisfy the same sort of relationship that the initial function satisfied. So in the case of, say, e to the x and natural log of x, if we graphed out f of x equals e to the x, and its inverse function, f inverse of x equals natural log of x, what relationship did we say these graphs have to each other geometrically? Jonah?
They're a reflection over y equals x.
Yeah, you could take one of these graphs and you reflect across the line y equals x, and you'll get precisely the other graph. Meaning if you look at this graph, you tilt your head 45 degrees, you allow for Dr. Gerstle to have poor art skills, so it doesn't exactly match up. But these two graphs should appear to be mirror images of each other across this line right here. Yeah, Lauren?
Could I get a packet, please?
Oh, did I not get the packets? My apologies. So, for instance, if we look at this function, if we wanted to take f of, say, 3, well, if f of x is e to the x, and we wanted to take f of 3, what we would get is, by definition, e cubed. But according to our inverse function rules, where f of a equals b means f inverse of b is equal to a, what would we expect to get then if we took f inverse of e cubed? Bethany?
3.
Yeah, 3. Here, 3 3 is like taking the place of our A, E cubed is taking the place of our B. So F inverse, if F of A is equal to B, F inverse of B should be equal to A. And that's in fact how we even define the natural log function. We can define the natural log as being a function that takes E cubed to say 3. Where if e to the A is equal to B, natural log of B is equal to A. And in that sense, we say that e to the x and natural log of x kind of are opposites of each other. The x and y coordinates for one become the y and x coordinates respectively in the other. Any questions or comments thus far? Yes, I think.
Could you even say that like the inverse function is almost like swapping out x for y?
That's a great way to describe it. You're swapping what the role of your x coordinate and your y coordinate. Where for f, if we treat a as being an x and b as being a y coordinate, the old y coordinate becomes the new x coordinate, and the old x coordinate becomes the new y coordinate, so to speak. So for instance, if we look at f of x equals e to the x, 3 comma e cubed is a point on the graph of e to the x. But if we want to look at what's the corresponding point on the graph of natural log of x, it would be the point e cubed comma 3 instead. All of our xy points just have their coordinates swapped going from one function to the other. So Dr. Gerstel, how does this relate back to trig functions? You said we're going to be talking about inverse trig functions in here. Well, same idea. We want to define, let's say we wanted to look at sine of x as being our new f of x. I don't know why I wrote sine of x before the f of x, but I'm sticking with it. Good old sine of x. Like cosine, sine of x has this nice oscillatory wave pattern to it, where it's constantly going between -1 and +1 as far as y values are concerned. And it's alternating between 0, 1, 0, 1, 0, -1, 0, 1, 0, -1 at multiples of pi over 2. That our graph of sine of x would look something like this. If f of x is equal to sine of x, according to this graph, what would f of pi be equal to? A?
0.
Yeah, f of pi would be equal to 0. So if we wanted to flip that around and say swap our x and y coordinates, what would that tell us that f inverse of 0 should be equal to? If we're trying to define a new inverse function where we swap x and y coordinates. James?
Pi.
Yeah. If our inverse function just takes an xy coordinate pair like pi comma 0, it's going to swap it to make 0 comma pi. So, looking at this graph, Joy, what would you say that f of 2 pi should be equal to?
0.
Yeah, f of 2 pi also should come out to 0. So if we do our old switcheroo on our x and y coordinates, what would that tell us f inverse of 0 should be equal to? 2 pi. And Taylor, if we look at this graph, what would we say that f of 0 should be equal to?
0.
Yeah, the y coordinate of 0. So according to that, if we swap our x and y coordinates around, what does that tell us f inverse of 0 should be?
0.
Should be 0. Swapping our x and y coordinates actually doesn't really require much there. They're both 0. Does anybody see a problem here? Or what issue do you see?
It fails the vertical line test, so it can't be a function.
How does this fail the vertical line test
You have multiple y coordinates.
for the same x coordinate? Yeah. If f inverse of x is a function, can f inverse of 0 be equal to like 3 different things? The idea behind a function is if you plug in a single input, you should get a single output. And yet if we were trying to define a function like, say, f inverse of x, which we're going to denote as being inverse sine of x like this, can inverse sine of 0 be equal to pi, 2 pi, and 0 all at the same time? Carson? Doesn't look like it. So we have an issue. Inverse sine of x would appear not to be a function. Technically, we could even say something like f inverse of 0 is equal to 3 pi, because f of 3 pi is 0. F inverse of 0 would have to be equal to 4 pi, since f of 4 pi would be equal to 0. F inverse of 5,786,192,725 pi would be equal to 0, so f inverse of 0 should be equal to whatever monstrous multiple of pi I would say. Technically, there are infinitely many x coordinates. Any multiple of pi that'll give us a y coordinate of 0 on our sine of x graph, which would tell us that f inverse of 0 would have to be equal to infinitely many things. And that's distressing / sad, if you ask me. Any questions or comments thus far? So how do we get around this? How can we define an inverse function for sine of x if sine of x would have to have an inverse where f inverse of 0 would have to be infinitely many things? James?
You could set it in a certain form to where it gives you every single output that it can give you.
Set it in a certain form. Say that again? Sorry.
So you can make the inverse function equal to like something that's in the form where it can give you every output.
Okay.
So for this one, you would multiply pi by any integer, and it will give you every single output that it could possibly be.
Holy moly. Multiply pi by 8. So we're basically saying, we're going to treat pi, 2 pi, 3 pi, 4 pi as all being the same.
Well, it's just a way to list it out of what it can be.
Oh, I see. You're saying write f inverse out as a set of values rather than just
Yeah.
a single value?
Mhm.
We could do that. That sounds painful. I don't want to have a function that maps single values to entire sets of values. I'm teaching that right now in my 400 level real analysis course, and even they can't handle that very well. That's being mean to them. They can't handle that very well yet. So James, what you suggested is totally a valid way to get around this. It sounds scary, and it's not the approach I would particularly like to take if we can avoid it. So, Emerson, if we look at our graph of sine of x, what do you notice is the range of this function? Meaning, what are the y values that sine of x can actually produce as outputs?
It's all between -1 and 1.
Yeah, you notice all of our outputs lie between -1. That's not -1, that's +1. I know the difference between positive and negative numbers. I'm a math professor. And -1. All our y values, assuming, I actually drew my graph correctly, lie between those two y values. So our idea for getting around this issue, if you notice, we can find an interval of x values where sine of x is going to take on every value between -1 and +1 exactly once. Right now, if I were to ask you the question, find all the x coordinates where y is equal to 0, you would say, oh, it happens here, and here, and here, and here, and here-ish, and infinitely many other points. But our goal is going to be, our idea is going to be to restrict the domain of the function f of x equals sine of x to where sine of x takes on all y values in the interval from from -1 to 1 exactly once. And to do that, well, there's actually a lot of ways to pick an interval over which sine of x will take on all y values exactly once. I'm going to pick this interval. From pi over 2 to 3 pi over 2. Because if we look at the interval of x values from pi over 2 to 3 pi over 2, we get every y value from +1 down to -1. Yes, I wanted the difference. But each y value over this interval is only going to occur a single time. There's going to be exactly one x coordinate between pi over 2 and 3 pi over 2 that'll have a y coordinate of 0, or 1, or a half, or -1/3. Or square root of 3 over 2. So in other words, we're going to restrict our inputs to the interval from x goes from pi over 2 to 3 pi over 2. And what we're ultimately going to do is we're going to say for sine of x, in order to find an inverse function, inverse sine of x, what we're going to say is we're going to let inverse sine of x give us all, has to get and say, take f inverse of, say, something like, also, why am I saying pi over 2 to 3 pi over 2? We're going from -pi over 2 to pi over 2. That's what happens when I try and teach without looking at my notes at all. Okay, sorry, I said that wrong, but it's the same idea. If you look at all the x coordinates from -pi over 2 to pi over 2, we're going to take on every y value between -1 and 1 exactly once. So then, if we wanted to say what is f inverse of 0, we're going to say f inverse of 0 is the x coordinate in the interval from -pi over 2 to +pi over 2, satisfying f of that x coordinate is equal to 0. So Devin. If you look, we found a way to generate a lot of different values of x, like pi, 2 pi, 0, negative pi, etc., that are going to give us 0 when we plug them into sine of x, right?
Yes.
Cool. Which one of these x values that's giving us an output of 0, which of these x values is going to be in the interval from negative pi over 2 to pi over 2? Pi, 2 pi, or 0?
2 pi.
Is 2 pi in between negative pi over 2 and pi over 2?
It is not, no. Pi.
So- Is pi between negative pi over 2 and pi over 2?
It's between pi over 2.
And 3 pi over 2. So the question I'm asking is, what's the x coordinate of the point in this kind of interval of x values? Which x value in here is going to give us a y value of 0 when we plug it into sine of x?
Pi over 2.
No, pi over 2, we plugged in pi over 2 as an x coordinate, it's going to give us a y value of 1.
Just pi.
No, pi's outside that interval. Emerson, help him out. What x?
Negative pi over 2 to pi over 2 is going to be 0.
Yeah, I think 0 is the x coordinate we're looking for, because 0 is in between negative pi over 2 and pi over 2, and 0 still satisfies that if we were to take f of 0, we would get 0 as an output. I.e., f inverse of 0 would have to be equal to 0 specifically. How about f inverse of 1? Bethany?
Pi's house.
Yeah. What x value between negative pi over 2 and pi over 2 is going to give us a y value of 1? Pi over 2 would. It's a point that's in between, that's in the interval from negative pi over 2 to pi over 2, and it would satisfy that f of x equals 1 there. So we could say f inverse of 1 is pi over 2. Since x equals pi over 2 is going to be the unique x in the interval from negative pi over 2 to positive pi over 2, satisfying f of x is equal to 1. So let's write some of this down. So what we're going to say, here I'm going to be on the second page, is that in general, we can say that y equals inverse sine of x is going to be the unique angle in the interval from negative pi over 2 to pi over 2, such that sine of y is equal to x as a general rule of thumb. Meaning, if we want to find inverse sine of 0, we need to find what's the x coordinate between negative pi over 2 and positive pi over 2 that has a y coordinate of that sine of that point is 0, well, that would occur in x equals 0. What's inverse sine of 1? Well, that's the x value between negative pi over 2 and pi over 2 that when we plug it into the sine function will give us 1. Well, that's pi over 2. Pi over 2 is the only x value between negative pi over 2 and pi over 2 that when we plug it into the sine function will give us 1. Dr. Gerstle, I'm tired. I hate trig functions. Trig functions have always been the bane of my existence. How many of you would agree with that statement? I appreciate the honesty. Dr. Gerstle, does that mean we're going to have to memorize the unit circle again and remember all of the angles from like what is sine of pi over 6, what's cosine of pi over 3? It does not mean that. Anytime I require you to know some trig functions from here on out, I'm going to give you a handy trig sheet. So if you flip to the back page of the packet, I'm actually going to give you a unit circle. So if I were to ask you the question, say, of what is cosine of pi over 6? Well, you could go to pi over 6 on the unit circle and see, I need the x-coordinate of this point. Aha, cosine of pi over 6 is radical 3 over 2. Or if you wanted to find the sine of 2 pi over 3, you'd go to 2 pi over 3 on the unit circle and say, aha, sine of that is at this point's y-coordinate. It's going to be square root of 3 over 2. I will give you this unit circle on any time you need to use trig functions from here on out. That being said, you will have to know how to read this unit circle. I expect that if I give you a copy of this unit circle and say find cosine of negative pi over 6 or find tangent of pi over 4, that you would be able to do that using this unit circle. Everybody cool? All right, have a good one, everybody. We will continue our discussion then on in Friday's class.